They're actually two talks back to back, so I just melted them into each other, trying to keep it short and sweet. It's also going to be very low level, but you knew what you signed up for when you came to this hackathon, right? Does this keyboard not work? Yeah, okay, nice. So I'm going to try and briefly cover the whole history of the entire mess, basically, in Python, just basically for context and for us to make wise decisions regarding surf. So it starts with the C++ developer called Guido van Rossum, who basically wanted a higher level human readable language for the business logic. And the problem was that he still needed to use the existing C and C++ libraries for computation. Otherwise, nobody would have started using this new language he came up with called Python. So initially, there was this thing called C types, and that is technically a foreign function interface, or FFI, which is a fancy way of saying it's just a hack to be able to call C++ from Python. And people still use this to this day. I mean, like even a couple of days ago, the org came up with the square array thing, which also uses C types. And it's just quick and simple, and it works, right? So if you have a compiled library, which is completely unaware of Python, like some library on your path called libmyexperiment, you can directly load that into Python from the path. And you do have to define some metadata. The way I like to think of this is effectively the same metadata you would get from a header file. You have to rewrite that in a Pythonic way. I'm honestly not sure why you can't just directly read in a header file that can understand this, but whatever, this is a choice. And if you do want to then call the function, you need to also cast everything to C types. So if you have a NumPy array, it is aware of C types. It has a C types interface. So you can cast things to like a float point number. Even if you want to pass in something as simple as an integer, you still have to cast it first to a C types kind of object. So the function signatures and call methods look a bit annoying, but that's what we have. At least it works. And basically, the correct way of doing things, which exists nowadays in Python as well, is the CPython API. So it looks a bit more annoying. There's more boilerplate, and now we write the wrapper in C rather than in Python. So one thing you need to know in Python is everything is a Py object. So if we have a function called myfunc, args over here is actually the tuple of arguments that we're passing into the function. And we just unwrap everything from there. So we start off with this args tuple, and we then parse the tuple. And we specify a format string of just O, which just means we're expecting a single Python object in our tuple. It's not multiple arguments, there's just a single argument to our function, which we're then assuming is a NumPy array, and we're using the array object header from NumPy to extract information. So we're expecting a float32 type array, and we can extract the data pointer and the shape and size and things. And NumPy should handle some amount of error handling for us. So if it's not a float32 type thing, it should print a helpful error in Python. In this case, all we're doing is in place doubling all of the elements in the array. So that's our actual computation, and the rest of this is all boilerplate, which is kind of annoying, and it's not even all of the boilerplate that we need. So Python can't even import this yet directly. What we also need is more metadata. So we're defining a module that Python will be able to import. That's the name of the module, myExperiment. We have to manually specify the function name. In this case, we're saying it's a function that can take in a variable number of arguments. None of them are keyword arguments, they're positional arguments. In this case, it's actually only one argument, but the NumPy array. We can specify a doc string. And if we now compile all of this, it will result in something that Python can directly import. So you'll have a library somewhere in your path called myExperiment, and Python can directly import that. And you can even run help on the functions that it contains, and it's printed out the doc string that we wrote in C. Now, the problem is still we had to write a lot of boilerplate, and even the boilerplate that we did write in this example used NumPy. So it's a NumPy specific example right here. So if we want to support Torch or TensorFlow or even built-in Python lists, we'd have to rewrite this code. So in order to solve that problem, Python has the buffer protocol. Now this basically predates NumPy and all of the other libraries out there, and it's natively supported by all of them. So the buffer protocol is a subset of the CPython API, and it's effectively a specification. So if you have a data container, it could be a surf data container, a torch tensor, it doesn't matter what it is, provided it provides a struct that contains some basic information, like a pointer to the actual underlying data and the shape and size, then Python will be able to understand this and read it in, and you can manipulate it. And all of the libraries basically support this. So here's an example of what that looks like. I know it looks like a lot of boilerplate still, but this only has to be implemented once by, let's say, the surf data container. So within the struct, you specify the pointer to the data, and yes, this is intended to be contiguous. You specify things like strides, which is basically how you differentiate between C and Fortran contiguous memory. But you might be able to abuse this for non-contiguous things. Arrays of arrays, maybe. I wouldn't necessarily recommend it. I know Surf does have arrays of arrays, but they should be contiguous now, maybe, going forward. Anyway, so this is the new version of the Python wrapper now that, again, we expect a tuple. And we parse that tuple, but in this case, instead of O as a single object, we now have this W star format, which basically means we expect a buffer. So this buffer thing could be from a NumPy array, but it could be from a Python list, it could be from a torch tensor. And from that buffer, we directly access the data pointer. Again, we're still just doubling all elements in place. And for memory management purposes, we have to tell Python that we're now done using this buffer. So in case nobody else is using it, you can delete it. So the nice thing about this is, yes, it's now generic. It will run with anything that supports the buffer protocol, which basically is any series library. So NumPy, PyTorch, TensorFlow, hopefully soon things like SIL and Surf. So everything we've covered so far was assuming C, but we can reduce the boilerplate even further if we use C++, basically. So here's an example of what that looks like in PyBind 11. So this is a fully self-contained example. There's no other hidden things here, so this will directly compile. So we directly expect a buffer for our function and access the pointer. We can even throw C++ style exceptions, which will be caught and printed nicely in Python in the traceback. And yeah, so I mean, we still specify the function name and a doc string, and this just compiles directly. Any questions so far? No? Okay. No.
Yes. You have a float pointer buffer, yes. But so at the moment, this doesn't know if it's on GPU or whatever. So
it doesn't yet.
You're coming to that.
Yes, we'll come to that.
Yeah.
Good question. Yes. So this will catastrophically fail if it's not a floating point buffer, for example. Yeah.
Nikos has got a question.
Nikos, yes.
Yeah, does this support templates?
PyBind 11? Or
yeah,
I mean, this does support templates, yes, and I do make heavy use of them. So I mean, you could have a function that applies to floats as well as doubles and integers and that sort of thing. Yeah, you only write it once. Yes.
All right, thank you.
Indeed. Okay, so a completely different approach to passing around things is using this thing called the CUDA array interface, which the number people came up with originally. I might minimize this for people here. So it's effectively a Python level equivalent of the C buffer protocol, and I really don't understand it. So, I mean, effectively, instead of, let's say you're developing your code in C++, your heavy computational code, and you intend an external library that's also writing in C++ to use your data. Instead of just passing them your struct buffer thing, you're going to first wrap it in a Python dictionary, pass them the Python dictionary, then they have to extract the metadata from the Python dictionary and recreate a struct themselves. That's basically what this CUDA array interface thing is, which seems like a bad idea to me. But I mean, for your information, this is what it looks like. A few libraries do make use of this. So you construct this dictionary thing, and I mean, this is the entirety of the metadata that's contained within the dictionary, and things like this memory address is actually an integer. So the consumer of this will have to cast that integer into a void pointer and then a float pointer, I guess, to extract the data. It's very clunky, but whatever. So a slightly better version of that is DLPack. This does make sense because it does contain more information. So it's similar to the CUDA array interface, but it does handle ownership of the data, so reference counting. And also, if you have multiple GPUs on your system, or you're doing multiple streams, so it's a bit like partitioning a single GPU into virtual GPUs. If you're doing that sort of thing, then this can also take care of it for you. So this it's lots of boilerplate, but this is what it would look like if you implemented it using C types. Again, in my opinion, all that they should have done is maybe added a couple of fields to the C Python buffer protocol to specify device ID and stream ID. But yep, they came up with the spec. Again, people use this. So yeah, complete change of pace.
This is written in Python.
This is written in Python, but usually people supporting the LPAC will implement this in C. This is just an example of what it might look like in Python. Yeah. I think it was H5pack or something that I copied this code from, basically. Everyone has their own different implementation for it. In fact, if you go to the reference implementations link over here, you'll find a few examples from different libraries, and every single one of them does it differently. NumPy does it in C++. Yeah, I think, it was HiDep, I think, that uses C types. Yeah, that's where I copied this example from. This Python implementations, it's just, yeah, have fun with XLA as well. So, right. Complete change of pace. This is a bit of a tangent, but we will come back to this, and you'll see why this is relevant, which is CUDA unified memory. So if we want to do stuff on the GPU, we care about pointers that are accessible in the GPU. So a quick recap of CUDA for maybe some of you not that familiar with it. There's a difference between stuff that we can access on your host or CPU RAM versus your device or GPU RAM. So you can't directly access data. You have to manually copy data between the two. So assuming you have some data that exists on your CPU up here, you have to first allocate the same amount of memory on your device GPU, then manually copy all of the data. Only then can you execute a function that is meant to be running on a GPU. In this case, it's called a kernel. That's just the naming. You then wait for that kernel to finish before you start copying all of the data back again from the GPU back onto the CPU. And again, you need to wait for that operation to finish before you're going to start, I don't know, the rest of your Python program. And of course, you can free your temporary allocated GPU memory. So if you're going to call this every single time you want a CUDA function to be executed, that means you're constantly allocating and deallocating temporary data and copying data back and forth. But that's the state of things. Now, unified memory made this a lot easier to do. So instead of manually managing GPU and CPU data separately, we have this function called CUDA malloc managed. And what that does under the hood is it still reserves memory both on your CPU and your GPU, but it takes care of that memory reservation. If you don't have enough memory on both at the same time, this will immediately throw an out of memory error. But what you get out of it is a data pointer that you can just access on the CPU. So this is just a normal CPU function setting and accessing data. And if you then try and use that data pointer on the GPU, CUDA will kick in and it'll realize that, oh wait, this is actually normally before unified memory, it would have just crashed. You're accessing a data pointer that doesn't make sense on a GPU. Whereas in this case, CUDA will kick in and will say, oh wait, we need to copy the data from the CPU to the GPU and then translate the memory pointer into something that the GPU kernel will understand. So the nice thing about this,
it allocates anyway.
It definitely allocates the moment you run CUDA malloc managed.
Right.
Yeah. And if after executing this kernel, by the way, if something, and the synchronization, if something else then starts accessing the data on the CPU, CUDA will then again kick in and say, oh, wait, even though this is a CPU pointer, we just launched a kernel using it, so we need to copy the data back again onto the CPU.
Casper, do you know if it still works? Because I remember at the beginning there was a problem Windows versus Linux. The unified memory kind of didn't work exactly the same way. Is that still the case? Or?
It should work exactly the same way.
Oh, right.
But yeah, we shall not speak of esoteric bugs. In theory, it works the same way, yes. The nice thing about this, in addition to having less boilerplate code and less scope for errors, it could also do interesting interleaving. So it might be able to copy half of the data and start executing your functions while the rest of the data is being copied. It could do intelligent stuff like that. So
But
Yeah.
you still need to synchronize.
You still need to synchronize if you're about to do some stuff in Python, because Python might not be aware of your CUDA functions and when it's allowed to
Oh.
use the data, right? So yeah, you still need to synchronize at some point, I think. So to try and tidy up all of this, I basically created this library called CUVEC. The reason why I did this is because, again, C++ templating should make this a lot easier. So I'm sure most of you who have used C++ definitely know what a standard vector is. And the first template argument to a standard vector is the underlying data type. So are you using floats or doubles or integers? But what you might not know is nowadays we have a second template argument for a standard vector, which is effectively the allocator that you're going to be using for the data. Now, the default is just a malloc and free, but there's nothing really stopping you from using a CUDA malloc manage. And I really have no idea why nobody else seems to be doing this. It seems like a very obvious use case. So that's effectively the secret sauce of CUVEC. That's what it does under the hood. So you get something which really is a standard vector, which means it has all of the standard vectors methods. I don't have to re-implement them. So you can use the data method to get the underlying contiguous C-style pointer. You can check the size. You can even resize it. If you resize the vector, it's going to use the allocator that we defined, the CUDA malloc manage. So everything just works. So accessing these CUVEC things in Python basically uses the buffer protocol because it's built into Python. Everything should work. And once I extract the buffer within Python, I can then wrap that within a NumPy array because NumPy understands buffers. And NumPy will produce an ND array without having to do any memory copies. So you also get all of the underlying functionality of NumPy itself. So the case study for that was NiftyPet, which is something that Pavel initially developed. It's a tomographic imaging reconstruction software, specifically for Siemens Biograph NMRs. So it has forward and back projectors for PET. And originally that used NumPy arrays, which were then exposed using the CPython API into C++ land. And then we, in CUDA, every single time we called the forward projector, we would do this malloc temporary memory on the GPU, copy the memory over, execute the CUDA kernel, copy the memory back, and then deallocate the temporary
It's
memory.
It
still does this for some things, yes.
Yes, and that is for Windows is separate than for Linux still.
It's awesome. This is the problem when we do
ugly.
science rather than engineering, right? But the science works, right?
Supposedly.
Yes. So with CUVEC, basically now we just directly use these CUVEC array things and still use the CPython API, but we don't have this spurious temporary mem copies and also the allocations and deallocations. The reason why this works, so the pull request implementing CUVEC instead basically deleted code. It didn't really add any code, which was, I mean, always a good feeling as a developer, right? Just deleting things. And the reason why this works is CUVECs really are standard vectors. They really have contiguous memory under the hood, and they really are NumPy arrays. So all of the Python code in NiftyPet that was expecting NumPy arrays still just continue to work. So
So NumPy is actually acting on that memory block.
yes, because NumPy can use CUDA malloc manage pointers because they just work on the CPU as well. So
Right.
if you want to see a minimal example of that, you don't even have to look at NiftyPet. You can use numQ, which is something that NiftyPet uses also under the hood, which is just very basic matrix operations. I think it's element-wise multiplication, addition, and division, and that's it. But it's a very minimal wrapper that uses CUVEC and the CPython buffer protocol if you want to take a look at it. I think that's pretty much all I wanted to cover. I mean, as a quick bonus, I can mention packaging, but yeah. Any questions so far?